Hello everyone. We'll talk about the sunrise pattern and the mathematics behind that. This picture has become very popular in social media, and what is shown over here is sunrise has been captured starting from winter solstice to every next month, and for the entire year this has been done. Now the terrestrial pattern, terrestrial object seen in the picture give us the reference, and with that particular reference you see that the sun is shifting towards north. As we are facing east, on the left hand side is north and on the right hand side is south. So on winter solstice days the sun seems to be rising on the rightmost point, which is the southernmost point, and then here on the equinox day, the vernal equinox day on 21st March, the sun is rising exactly east, and then as we move further, okay, every next month the sun starts rising north of east, and this is the winter solstice day when the sun is going to rise the most north point from the east, and again it will start shifting towards south. Okay, as we can see here in this picture that it is moving towards the right hand side. Okay, now on vernal equinox day as well as on autumnal equinox day it is going to rise exactly east. On summer solstice it is going to rise the northernmost point of east, and on winter solstice day it is going to rise the southernmost point of east. How this pattern looks like, what is the mathematical expression behind this? Okay, that is what we are going to see here. Now we know why this happens. The Earth's axis is tilted, okay, and this tilt is relatively fixed. So Earth moves around the sun almost uniformly. That means this motion, okay, around the sun is almost uniform. In reality it is slightly elliptical motion, but the eccentricity is very small, and therefore in the first approximation we can nicely assume that it is almost a circular motion. One revolution corresponds to one complete year, and the tilt of the Earth's axis remains fixed in the direction during this month. So you can see that the tilt is this way, and over the entire year the tilt remains the same. On equinox day it is neither towards the sun nor in the opposite direction. So on vernal equinox as well as on autumnal equinox, that is on 21st of March and around 21st to 23rd of September, the positions are like this. On summer solstice day in the northern hemisphere, the sun, the axis is tilted towards the sun, and on the winter solstice day in the northern hemisphere, that happens on 22nd of December, you can see the northern hemisphere is tilted away from the sun. Now we'll see how this causes the relative motion of the sunrise shifting as in different mathematical steps. So sun's apparent motion is along the ecliptic plane, and the Earth's rotation, okay, Earth's rotation axis, if you consider, perpendicular to that is the equatorial plane. Okay, so this plane is called equatorial plane, and the revolution plane of the Earth, as seen from Earth, apparently the sun will be revolving, so that plane is called ecliptic, and it is shown here with this particular dotted circle. So the Earth's revolution around the sun causes sun's apparent motion along the plane called ecliptic, and the apparent motion of the sun is measured with coordinate lambda, so the celestial longitude lambda, and it is measured from vernal equinox. So as sun is apparently moving uniformly, the lambda is changing almost about 1 degree per day. It measures how much it has moved from point of vernal equinox, and on vernal equinox then lambda will be 0. On summer solstice the lambda is going to be 90 degree. On autumnal equinox the lambda is going to be 180 degrees, and on winter solstice this lambda is going to be 270 degrees. And again on vernal equinox it will complete 360 degree, which you can count again as 0 degree. Now this diurnal motion is due to Earth's rotation. Now what is diurnal motion? The motion of the stars observed over the entire night, and we can see that here that how this motion is there. So here we are looking at east now, and this is the blue line shown over here represent the equatorial plane, whereas the other line shows the ecliptic plane, and you can see that ecliptic is changing. Okay, and if you look towards north now, you see all stars seem to be moving around the pole star, and then towards east, towards west, if you go, you see the ecliptic plane is like this, and all the motion of the star is parallel to the equatorial plane. Okay, the ecliptic position can keep changing, its orientation changes, but equatorial orientation remains the same. Okay, and if we move towards south, then you will see again that all stars seem to be moving about the southern point. Okay, so here you could see all stars are moving parallel to equator, and in the south you see that all again the motion is going to be like circular motion. Everything is moving effectively around the southern pole. Now, in order to measure these motions, we define different coordinates. So, apparent motion of the celestial bodies from the earth can be measured with different coordinates from any particular location on the earth. As you have seen in the earlier picture, the orientation of the equatorial plane remains the fixed. Okay, and during diurnal motion, the orientation of the ecliptic seems to be changing. Okay, ecliptic is the plane in which apparent motion of the sun is happening over the year. That is basically the plane of revolution of earth around the sun, whereas equatorial plane is the plane which is perpendicular to the rotation axis of the earth, which is fixed in the space, and therefore equatorial plane is fixed in the space, and therefore if you are standing on a particular point on the earth itself, the equatorial plane is going to remain fixed. Now, it is useful to calculate sun's coordinate with respect to equatorial plane in different months, because sun is going to be on ecliptic, and ecliptic orientation can change, and for that the important coordinate is declination. What is this declination? It is the angle of the object or any object, celestial object, it could be sun, from the equatorial plane. So, if an observer is standing over here, this is the north direction and this is the equatorial plane, and if the object is at this point, then angle subtended by the object with equatorial plane is called angle of declination, and this angle of declination will be positive if the object is in the northern hemisphere, it will be negative if the object is in the southern hemisphere. If the object is exactly lying on the equatorial plane, like for example sun lies on the equatorial plane on equinox days, that time the declination is going to be 0. Now, we will see how declination of the sun changes over the year. So, there is a way you can convert the coordinates which are used in equatorial coordinates and ecliptic coordinate. What is equatorial coordinate? The angle measured from the equatorial plane, and ecliptic coordinates are the angles measured from ecliptic plane. So, there is a relation which can be given like this: sin delta is sin beta cos epsilon plus cos beta sin epsilon sin lambda, where delta is the declination, that is angle measured from equatorial plane. Lambda is the celestial longitude. We saw that it is angle measured along the ecliptic plane, and it is changing uniformly. So, every month the sun is going to change longitude by 30 degrees, and epsilon here is 23.5 degree. It is actually angle between the equatorial and ecliptic plane. That is nothing but the tilt of Earth's axis with revolution axis. So, that is 23.5 degree approximately. And beta is the celestial latitude. The way you have declination, angle measured from equatorial plane, there is celestial latitude, which is angle measured from ecliptic plane. But for sun, it is 0 because sun is on ecliptic plane, and therefore beta becomes 0 always. Now, if you substitute this beta equal to 0 here in this formula, sine of 0 is 0, and therefore this term vanishes. Cos of 0 is 1, and therefore this term becomes a small simple term, and we get relation sin delta is equal to sin epsilon sin lambda. Now, if lambda is changing uniformly, how delta will be changing? That can be plotted, and you can see the declination of the sun varies like this. This is a nice sinusoidal curve. The vertical axis here is the declination axis, the horizontal axis is the days, okay, and starting from the 1st January we are counting these days. So, you can see here around 21st of March, okay, we get lambda equal to 0 degree, okay, and that lambda equal to 0, we also have declination equal to 0 here, okay. On summer solstice day, the lambda becomes 90 degree, and that is approximately about 180 days from starting of the year. Okay, and the declination here is maximum, and then if you go to autumnal equinox, the lambda is 180 degrees. Okay, and declination again becomes 0. And if you come to winter solstice, the lambda is 270 degrees, that is almost near the end of the year on 22nd December, and the declination of the sun is negative, it is almost minus 23.5 degrees. So, declination of the sun varies from minus 23.5 degrees to plus 23.5 degrees, okay, and the motion is almost sinusoidal. Now, shifting of the sun over the year can be seen based on this. Here is the position of the sun on one particular day. This is this particular picture is taken from the Stellarium app, that how the sun might look on 22nd December, and you can see the sun is far away from this equatorial plane. So, this angle is the declination angle, and it is largest, it is 23.5, and it is towards south. Now, what we can see is how this every month is going to change. So, there will be 12 pictures, and you can see that now it has shifted. So, after 1 month the declination has reduced, after 2 months it has further reduced, okay, and on 21st of March you see the sun is almost on equator, it is equinox. Okay, then next month the sun has shifted, that is, this is in April further, and in May it has gone further north, okay, and June it will be the northernmost position. Similarly, again in July it will come back towards south, okay, and in August it will further come back towards south, and in September it is going to be again equinox day, and the sun position is going to be exactly on equator, it is going to rise exactly at east, and in October it will shift to the south, November it will shift further south, and December is going to be the southernmost point, and this entire pattern is going to repeat, and that is what one can observe. So, if you have patience, you can capture it over entire year. Now, in order to know how much it will shift to the northern side or on the southern side of exact east, we need to understand the observer's coordinate. When we are measuring any celestial object, want to define any particular object's position, we use two different coordinates. One coordinate is called altitude, which is angle measured from the horizon, okay, and the second coordinate is called azimuth, that if there is an object over here in the sky, you take a perpendicular on the horizon and you measure at what point this perpendicular is going to drop from the north towards the east. That angle is called azimuth. So, if the object is exactly in the north direction, the azimuth is going to be 0. If the object is exactly at east, the azimuth is going to be 90 degree. If the object is exactly at the south, the azimuth will be 180 degree, and if the object is exactly in the west direction, then the azimuth is going to be 270 degree, and so on. So, we are going to see then that at sunrise what is the azimuth of object over the entire year, and we expect that it is going to be sometimes less than 90 degree when the sun is going to rise in the north direction, north of east, and sometimes it is going to be more than 90 degree when sun is going to rise south of east. Now, is there any formula to calculate this? Is there any formula which will give you the relation between declination and this azimuth? So, yes, there is a formula. Now, for that, simulating the motion of the sun, we need this particular formula. We need one more coordinate called the zenith angle, okay, and the zenith angle is nothing but a complementary angle to the altitude. Relation between declination of object and its observer coordinate is given by sin delta is equal to cos z plus sin phi plus sin z into cos phi cos a. We will see what are these terms. So, delta is the declination term here, z is zenith angle, and phi is the latitude of the place, and this capital A is azimuth that we have seen in the earlier slide. During sunrise, the sun is on horizon, so altitude is 0 because altitude is angle measured from horizon, and zenith angle, that is angle measured from zenith, becomes 90 degree because zenith is exactly over a point. So, what we have is zenith angle plus altitude adds to 90 degree. So, when altitude is 0, zenith angle is 90 degrees, And if you substitute this z equal to 90 degree in the formula, then we know cos of 90 degree is 0 and this term will vanish. Sine of 90 degree is 1 and the term will become simple, and the formula is sine delta is equal to cos phi into cos E. So phi is going to be the latitude of the place, and that is going to play an important role. The declination and azimuth of rising is going to help us in this case. Now see, this formula is mainly for rising or setting, because we have put already z equal to 90 degree. That means the sun is on horizon, and it is going to be on horizon when it is either rising or when it is setting. Comparing with the earlier equation that we had formed for declination and lambda, we can see that earlier equation was giving us sine of delta is equal to sine epsilon into sine lambda, where epsilon is 23.5 degrees and lambda is the position of the sun over the year. Okay, on our vernal equinox lambda is 0, autumnal equinox lambda is 180 degree, and so on. Now compare these two, and what we get? We get cos phi is equal to cos phi into cos A is equal to sine epsilon into sine lambda, which gives you cos A equal to sine epsilon sine lambda upon cos phi. As lambda changes, A is going to change. Epsilon is constant, phi for a given place is constant, and therefore sine epsilon cos phi is going to be constant. And what is going to change over the year is lambda is going to change over the year, and therefore the azimuth of rising is going to change. And we can plot this, we can do the calculation for this, and you can see here the calculation done, that lambda starting from winter solstice 270 degrees to 300 degree and 330 degrees every next month. So every 1 month lambda is changing approximately by 30 degrees, and then we see this kind of azimuth. You see here the azimuth has greater than 90 degree, which means the angle measured is more than 90 degree, or the object is in the south, and at winter solstice azimuth is maximum south. And then when lambda becomes 0, that is vernal equinox, azimuth is exactly 90, which means the sun is going to rise exactly at east. Okay, and when lambda is equal to 90 degree, that is summer solstice, the azimuth value is minimum. That means the sun is going to rise northernmost point from east. Okay, therefore angle measured from the exact north is smallest, and we can plot that graph, and you can see that it's a nice sinusoidal curve. We can also plot this horizontally, this particular graph, and see that is what is plotted over here as a bar diagram. This is only to show you that how the pattern of the sun in the picture will actually look like. So angle A is measured from the north to east. So as seen on the eastern horizon, increasing A will go towards right and lower A will be towards left. Okay, and we can see, compare this particular pattern with actual photograph of this. This is the pattern which is seen in the actual photograph. This is the pattern that we have plotted over here. This particular graph has been plotted for 8 degrees north, that is Kanyakumari location, and you can see the quite nice resemblance. So astronomical patterns can always be given by various mathematical expressions. Learning mathematics of astronomical objects is itself a joy. Thank you.